440 million years ago, something walked across a muddy shoreline on a continent that no longer exists, and it left footprints behind that hardened slowly into stone. Those footprints are still there today, pressed into rock that geologists can hold in their hands. Now imagine a different set of footprints, not from a creature, but from a civilization with cities, with machines, with fires that burned for centuries. Could such a thing have existed on Earth before us, and vanished so completely that not one piece of solid proof remains? This is why scientists at NASA and the University of Rochester actually sat down and asked this question seriously, not as science fiction, but as a real test of what the geological record can and cannot tell us, and the answer they found was far stranger than a simple yes or no. Before we begin, be sure to like the video and subscribe for more journeys into the cosmos. Now, take a deep breath, and let's begin. Picture the surface of the Earth as a book, an enormous book made of layered stone, with each page representing thousands of years pressed flat by the weight of everything above it. We are taught to believe that this book records the full story of life on this planet, that if something important happened, it left a mark, a fossil, a footprint, a layer of ash. But books can be edited. Pages can be torn out. And Earth has been editing its own book relentlessly for billions of years, folding pages into mountains, melting them into magma, and dragging entire chapters down into the planet's interior, never to be read again. The scientists who first proposed what has come to be called the Silurian hypothesis were not suggesting that a lizard civilization once ruled the planet, despite the playful name borrowed from an old science fiction show. Their question was colder and more precise than that. If an industrial civilization, complete with cities, agriculture, and machines, had existed on Earth tens of millions of years before humans, buried deep in a period long before recorded history, would we, today, with all of our satellites and drills and laboratories, actually be able to find convincing evidence of it? And when they worked through the physics, the chemistry, and the geology involved, they discovered something deeply unsettling. The honest answer might be no. To understand why, you first have to understand exactly how thin our own testimony to the universe truly is. Human civilization has existed in a recognizable form for perhaps 12,000 years. And industrial civilization, the kind that burns coal, smelts metal at scale, and reshapes the chemistry of an entire planet, has existed for less than 300 years. 300 years, against a planet that is 4.5 billion years old, is such a small sliver of time that if you compress the entire history of Earth into a single calendar year, our industrial age would occupy less than the final quarter of a second before midnight on the 31st of December. And yet, within that sliver, we have changed the isotopic ratios of carbon in the atmosphere. We have driven other species into permanent absence. We have scattered radioactive isotopes across every ocean, and we have manufactured materials that never existed anywhere in the universe before we made them. If our own footprint is this dramatic and this fast, then the question becomes almost mathematical rather than philosophical. Suppose a different technological civilization existed 50 million years ago, or 100 million years ago. And suppose it also burned fuel, altered the atmosphere, and eventually collapsed or transitioned to something we would not even recognize as industrial. What would 50 million years, or 100 million years, do to the evidence they left behind? The answer lies in one of the most humbling truths in all of geology, which is that the surface of this planet does not preserve time evenly. It preserves almost nothing, almost all of the time, and only rarely, almost by accident, does it preserve something extraordinarily well. Consider the ocean floor beneath you right now, wherever you are reading or listening from, because even landlocked places once sat beneath ancient seas. New ocean crust is being created constantly, at long ridges where molten rock rises from the mantle and spreads outward like a slow conveyor belt. That same crust, on the other side of every ocean basin, eventually plunges back down into the mantle at subduction zones, melting and recycling into the deep interior of the planet. The complete cycle, from birth at a ridge to death in a trench, takes roughly 200 million years on average. This means that almost none of the ocean floor on Earth today is older than that span of time. The vast majority of the ocean crust that existed during the age of early complex life on land has already been swallowed by the planet itself, erased as thoroughly as if it had never existed. On land, the situation is only slightly better, but not by much. Mountains rise and then are worn down by rain, wind, and ice, grain by grain, over millions of years. Entire mountain ranges older than the Himalayas have been ground down to gentle hills and then to flat plains, their material washed into rivers and carried to the sea, where it becomes sediment, and where it might, if conditions are just right, eventually become new rock. But most of it does not survive as identifiable rock at all. It gets mixed, reworked, buried, and metamorphosed until any trace of its original structure is gone. Geologists often say, half joking and half serious, that the rock record is less like a book and more like a diary that has been through a flood, a fire, and several decades of forgetful editing, with most pages missing entirely and the remaining ones smudged beyond easy reading. Now think about what this means for fossils specifically, since fossils are the primary evidence we would expect any past life, intelligent or otherwise, to leave behind. Fossilization itself is an extraordinarily rare event. For an organism to become a fossil, it typically needs to be buried quickly, in an environment low in oxygen, ideally underwater in fine sediment where it will not be scavenged, decomposed, or disturbed, before minerals slowly replace its original material over thousands of years. The overwhelming majority of living things that have ever existed on Earth left no fossil at all. Soft-bodied creatures, insects, most land plants, most land animals of any kind, they typically vanish completely within decades of their passing, leaving nothing behind except perhaps a faint chemical trace in the soil that erodes and disperses long before anyone could ever detect it. Paleontologists estimate that the fossil record likely captures a fraction of 1% of the species that have ever existed. Written as a plain figure, some estimates suggest we have found evidence of a number of species that is smaller than 1,000th of the total number that actually lived across the entire history of this planet. If entire branches of the tree of life can vanish so completely that not one species from an era survives in the fossil record, then a single species, even an intelligent, tool-using species with cities, could plausibly follow the exact same fate. The rock record does not care how clever a creature was. It only cares about geological chance, chemistry, and time. A civilization is not exempt from these rules simply because it built roads or wrote language. Time treats a city no differently than it treats a coral reef, and often it treats the coral reef more gently, since limestone endures far longer than concrete or steel. To figure out what an ancient industrial civilization might have left behind, the researchers behind the Silurian hypothesis did something clever. They started by asking what our own civilization is leaving behind right now, since we are, after all, the only industrial civilization we know for certain has ever existed. If future geologists, whether human descendants 10 million years from now or some other intelligence entirely, dug into the rock layers being formed today, what would actually survive long enough to be found? The most obvious signal is carbon, Since the beginning of industrial fuel burning, humanity has released an enormous quantity of ancient carbon back into the atmosphere. Carbon that had been locked away in coal and oil for hundreds of millions of years. This sudden release changes the ratio between different forms of carbon in the atmosphere and oceans, a ratio that gets recorded in the shells of marine organisms, in ice cores, and in layers of limestone. That shift is subtle, but it is real, and it is the kind of chemical signature that can persist in rock long after every city has crumbled to dust. It would not look like a building. It would look like a strange, brief anomaly in the ordinary chemistry of an ancient ocean, a spike that appears and then fades within a geologically short window of time. Then there is nitrogen. Modern agriculture depends on synthetic fertilizer manufactured through a chemical process that pulls nitrogen directly from the air and fixes it into a usable form on a scale nature never approached on her own. This has roughly doubled the amount of reactive nitrogen cycling through the biosphere compared to natural background levels. That nitrogen washes into rivers, into lakes, into the sea floor, and it leaves a mark in sediment layers that a future scientist with the right instruments could plausibly detect long after every trace of the fertilizer factories themselves had disappeared. There is also the matter of new materials that simply did not exist anywhere in the universe before human industry created them. Plastic is the most striking example. Some plastic debris, mixed with beach sand and melted by heat from fires or lava, has already formed a new kind of rock that scientists have started calling plastiglomerate. Given enough time, buried under new layers of sediment, compressed and cemented the way any beach sand eventually becomes sandstone, fragments of this plastic-infused rock could theoretically survive for an extraordinarily long time, chemically unlike anything the planet had produced before industrial civilization arrived. Radioactive isotopes tell a similar story. Nuclear weapons testing and nuclear power generation released isotopes into the environment that do not occur naturally in significant quantities. And while many of these decay away within decades or centuries, a few persist for tens of thousands of years, leaving a faint but genuinely unnatural fingerprint in soil and sediment layers laid down during this century. And finally, there is the extinction signature itself. The current rate at which species are disappearing is far higher than the normal background rate recorded throughout most of Earth's history, comparable in speed, if not yet in total scale, to the handful of mass extinction events that mark the boundaries between entire geological periods. A future geologist would very likely notice a sudden, sharp cutoff in certain fossil groups within an extremely narrow band of rock, a signature almost identical in shape to the asteroid impact that ended the age of the dinosaurs, except caused by something entirely different. Taken together, these signals form what scientists now call an Anthropocene boundary, a thin, chemically unusual layer that marks the arrival of industrial humanity in the geological record. It is real, it is measurable in principle, and laboratories around the world are actively debating exactly where to draw its official starting line. But here is the deeply uncomfortable part of the story. Every single one of these signals is thin. Every one of them depends on very specific rock layers, surviving intact for an enormous span of time. Layers that, as we already discussed, have a strong tendency to be destroyed, buried, folded, or melted long before anyone gets a chance to read them. The scientists needed a real example from the past, a moment in Earth's history where something released an enormous burst of carbon into the atmosphere very quickly, so they could compare it directly against what a hidden industrial civilization might have caused. They found their example roughly 56 million years ago, in an event known as the Paleocene-Eocene thermal maximum, often shortened to a simple acronym in scientific papers. During this event, global temperatures spiked dramatically over what appears, in geological terms, to be an extremely short window, possibly just a few thousand years. Carbon isotope ratios in ocean sediment shifted sharply, in a pattern strikingly similar to what modern industrial carbon release is doing to the atmosphere today. For decades, scientists have debated exactly what triggered this ancient warming spike. The leading explanations involve massive volcanic activity, releasing carbon dioxide, or the sudden destabilization of frozen methane deposits on the seafloor, which would have flooded the atmosphere with a powerful greenhouse gas in a geological instant. Neither of these explanations require anything remotely like a civilization. They are entirely natural processes, well understood within the framework of plate tectonics and ocean chemistry. But that is precisely why this event became such a useful thought experiment. If a natural process, with no cities, no factories, and no minds behind it, can produce a carbon signature that closely resembles what an industrial civilization would leave, then the presence of a similar signature somewhere else in the rock record cannot, by itself, prove that intelligence caused it. This cuts in both directions, and that is the part that makes the whole idea so intellectually uncomfortable. If we found a mysterious carbon spike from, say, 20 million years before the appearance of the first primates, we would almost certainly assume it was caused by volcanism or methane release, exactly as we assume for the ancient thermal maximum, because that is the far more probable explanation, and reaching for civilization would be an enormous leap without other supporting evidence. But the researchers point out something unsettling, hiding underneath that reasonable assumption. We would assume it was natural, largely because we have no other evidence to suggest otherwise, not necessarily because we could conclusively rule out every other possibility. In other words, the honest scientific position is not that we have proven no such civilization existed. It is that we currently have no evidence either way, and given how thoroughly the deep past gets erased, the absence of evidence here is far weaker proof than it would be for more recent events. The researchers were careful, and this point deserves real emphasis, to state clearly that they were not claiming any such civilization actually existed. There is no serial killer-style smoking gun hidden in some untouched layer of Eocene rock. Every other line of evidence we do have, the fossil record of mammals slowly diversifying after the extinction of the dinosaurs, the gradual and unbroken pattern of brain size increasing across millions of years in the primate lineage that eventually led to us, all of it points toward humanity being the very first species on this planet to develop industrial-level technology. What the researchers were doing instead was something more like a stress test on the scientific method itself. They wanted to know precisely how confident we are allowed to be in that conclusion, and precisely what kind of evidence would even be capable, in principle, of overturning it. Complex life has existed on land for a surprisingly long stretch of time, far longer than most people assume when they picture the history of Earth. Plants colonized dry land more than 400 million years ago. Insects took to the air not long after. By around 360 million years ago, vast, swampy forests covered huge portions of the planet, forests so extensive and so long-lived that their compressed remains still power much of modern civilization in the form of coal. Reptiles appeared. Then a spectacular diversity of dinosaurs dominated the land for well over 100 million years, a span of time so much longer than the entire history of mammals that it is almost difficult to comprehend emotionally, even once you understand it intellectually. Across that immense span, could any lineage have developed the kind of intelligence capable of building tools, controlling fire, and eventually developing industry? The honest scientific answer is that nothing in the fossil record suggests it happened, and there are good biological reasons to think it would be unlikely. Human-level intelligence, at least as far as we can tell from the fossil record, required an unusual and specific combination of traits that took an extraordinarily long time to accumulate, even within our own lineage, including complex social behavior, dexterous hands freed from the demands of walking, an omnivorous diet capable of fueling a very energy-hungry brain, and a very particular evolutionary pressure that favored ever larger brains generation after generation for millions of years, without being interrupted by extinction or environmental catastrophe. Dinosaurs, despite dominating the planet for an immense length of time, show no clear fossil evidence of this kind of runaway brain development in any lineage, though a few groups, particularly some of the smaller feathered dinosaurs closely related to modern birds, were developing notably sophisticated brains and behaviors by the time the age of dinosaurs came to its abrupt end. But notice the shape of the argument here, because it matters enormously. We are not saying it is impossible. We are saying we have no positive evidence that it happened, which is a fundamentally different and much weaker claim. And this is exactly where the Silurian hypothesis becomes uncomfortable rather than simply interesting. Even if some lineage, somewhere across those hundreds of millions of years, had developed industrial technology and then collapsed or transitioned away from it entirely within a few thousand years, the physical traces of their existence would face the exact same brutal erosion we discussed earlier. Their cities would erode. Their ocean floor evidence would very likely have already subducted into the mantle and been destroyed, especially for anything older than 200 million years. Their fossils, unless extraordinarily lucky, would have been one entry among the overwhelming majority of species that leave no trace at all. There is also a subtler possibility that the researchers raised, one that receives far less attention than it deserves. Not every possible civilization would necessarily follow the same industrial path that we did. Our own path depended heavily on the accidental availability of enormous underground reserves of fossilized carbon. Reserves that took hundreds of millions of years to accumulate and that we are currently burning through in a geological instant. A hypothetical past civilization might have developed differently, relying on renewable energy sources from the very beginning, building with organic materials that decompose without a trace, rather than durable metal and concrete, and never triggering the kind of dramatic atmospheric carbon spike that would leave a clear chemical signature in ocean sediment at all. Such a civilization could, in principle, have existed and left behind almost nothing detectable, not because it failed to exist, but because it simply never generated the kind of blunt geological footprint that we happen to be generating right now. If you wanted to actually go looking for evidence of an ancient industrial civilization, where would you even start digging? Scientists have proposed several specific targets that would be considered far more difficult to explain away as natural processes than a simple carbon spike. One of the strongest candidates involves synthetic molecules, chemical compounds that essentially never form through any known natural geological or biological process, such as certain complex plastics or industrial chemicals designed to resist breaking down in the environment. If a rock layer from tens of millions of years before humanity contained even trace amounts of a molecule that should not exist without deliberate industrial synthesis, that would be an extraordinarily difficult signal to explain through any natural pathway. Another strong candidate involves unusual isotope ratios of certain rare elements associated specifically with nuclear technology, isotopes that essentially never occur in meaningful concentrations without a nuclear reactor or a nuclear weapon creating them. Unlike ordinary carbon, which nature can produce through several unrelated processes, a manufactured isotope with a very particular radioactive signature would be a much harder thing for skeptics to wave away as coincidence. A third candidate, somewhat more indirect but still compelling, involves the depletion of specific metals in easily accessible surface deposits. Human mining has already stripped away much of the easily reachable, high-concentration ore deposits of certain metals near the surface of the planet, metals that took billions of years of geological processes to concentrate in the first place. A future civilization mining our planet after we are gone would find these particular deposits strangely picked over compared to what geological formation alone would predict. A bit like walking into a grocery store and noticing that only the shelves at exactly arm's height have been emptied, while everything higher and lower remains untouched. But here is the enormous practical problem underlying every single one of these clever ideas. And it is not really a problem of chemistry or physics at all. It is a problem of scale and sampling. Humanity has drilled directly into a genuinely tiny fraction of the planet's total sedimentary rock record. Deep-sea drilling projects, the most systematic effort ever undertaken to sample ocean floor sediment across geological time, have collected core samples from a comparatively small number of specific sites scattered across the entire globe. Each one a narrow cylindrical sample, only centimeters wide, pulled from an ocean floor that spans an area covering most of the planet's surface. Extrapolating confidently from such an extraordinarily thin sampling of the total available record to a sweeping statement, like nothing unusual exists anywhere in 50-million-year-old rock is, quite honestly, a much bigger leap of faith than most people realize when they hear scientists calmly stating that no prior industrial civilization has been detected. This is not an argument that something is hiding there, waiting to be discovered. It is an argument for intellectual honesty about the actual limits of what we have looked at. We have checked a small, scattered sample of an enormous archive, an archive that has already had many of its oldest pages torn out entirely by tectonic recycling, and within that small sample, we have found nothing unusual. That is meaningful evidence, but it is evidence with real limits, and pretending otherwise would be a kind of overconfidence that good science tries hard to avoid. Once you understand how fragile and thin the geological record really is, the implications stretch far beyond a single thought experiment about ancient Earth. They reach directly into one of the biggest open questions in all of science, a question usually called the Fermi paradox, named after the physicist who reportedly asked, during a casual lunch conversation, a deceptively simple question. Given how many stars and planets exist in our galaxy alone, and given how much time has passed since the galaxy formed, where is everybody? One proposed answer involves something called the Great Filter, a hypothetical barrier or bottleneck that prevents life from reaching a stage where it becomes a lasting, galaxy-spanning, easily detectable presence. Perhaps the filter lies far in the past, in the difficulty of life ever beginning at all, or in the difficulty of simple cells ever becoming complex ones. Or perhaps, and this is the far more unsettling possibility, the filter lies ahead of us, in the difficulty of any technological civilization surviving its own industrial adolescence for very long, before either destroying itself or transitioning into something so different that it stops, leaving an obvious, easily recognizable footprint. Now, combine that unsettling possibility with everything we just learned about how quickly and thoroughly a planet erases its own history. If technological civilizations across the galaxy tend to exist, on average, for only a few hundred or a few thousand years, in an easily detectable industrial phase, a blink of an eye compared to the billions of years available for life to evolve on a typical planet, then the galaxy could plausibly have hosted many such civilizations already, one after another, scattered across deep time, without any of them overlapping with us long enough for us to notice each other. Worse still, If a civilization existed and eventually vanished on a planet millions or billions of years before we developed telescopes capable of studying that planet's atmosphere in detail, any geological evidence of their presence would likely have suffered the exact same fate that ancient terrestrial evidence suffers here on Earth: buried, eroded, or subducted into oblivion long before anyone else arrived to look for it. This idea has genuine relevance for how we search for life on other worlds today. When space agencies send instruments to Mars, part of the mission involves searching not just for present-day biological activity, but for any chemical or mineral evidence of life, of any kind, from any point in that planet's 4.5 billion-year history. Mars had liquid water on its surface for a meaningful stretch of its early history, and its geological activity slowed down and largely stopped billions of years ago, meaning its surface, unlike Earth's constantly recycled crust, has preserved genuinely ancient terrain far better than our own planet has. If life, even simple microbial life, ever arose there and later vanished as the planet dried out, evidence might actually still be sitting on the surface, undisturbed for billions of years, in a way that would be almost impossible to find on the more geologically restless Earth. The search for ancient biosignatures on Mars is, in a very real sense, the same intellectual exercise as the Silurian hypothesis, except run in reverse, using a planet that preserves its past far more faithfully than our own restless, tectonically hungry homeworld does. It helps, at this point, to run the thought experiment forward rather than backward, because it makes the whole argument feel less abstract. Imagine that humanity vanished tomorrow, calmly and completely, with no war, no catastrophe, simply gone, and the planet was left entirely to its own devices. How long would it take before someone, or something, arriving on Earth would struggle to tell that we had ever been here at all? The first few centuries would actually be the easiest window for detection. Cities would stand empty, but largely intact, their windows breaking, their roofs failing, plants slowly working their way up through cracked pavement. Within a few thousand years, most wooden and unmaintained structures would have collapsed entirely, consumed by weather, insects, and plant growth. Steel would rust away within a similar span, especially anything exposed to open air and rain. Within tens of thousands of years, the vast majority of our built environment, every house, every office tower, every road, would have crumbled into unrecognizable rubble, quietly being absorbed back into soil and sediment. Some things would last considerably longer than most people expect. Deep underground nuclear waste storage sites, sealed away specifically to remain undisturbed for extremely long periods, would remain chemically hazardous and detectable for tens of thousands of years, possibly longer. Certain forms of glass and ceramic, remarkably resistant to ordinary weathering, could survive in fragments for a very long time if buried and protected from direct exposure. Stone monuments carved specifically to endure, the kind found on mountainsides and inside protected structures, could plausibly last far longer than steel or concrete, though even the hardest stone slowly wears away under wind and rain across a long enough span of time. Beyond a few million years, however, almost everything familiar about our civilization would be gone from the surface entirely. What would remain would not look like a city at all. It would look exactly like the subtle chemical signatures described earlier. An unusual spike in atmospheric carbon isotopes locked into ancient ice and ocean sediment. A thin layer with a strange excess of specific metals, a sudden and permanent disappearance of certain species from the fossil record, and perhaps, if very lucky and very well preserved, a scattering of plastic-infused rock along ancient shorelines, quietly waiting inside a layer of stone that a distant future geologist might eventually chip open with a hammer. Utterly unaware that the strange material inside it was manufactured, on purpose, by hands very much like their own. Even our satellites and the objects we left on the surface of the moon would eventually be affected, though far more slowly, since the moon lacks the weather, water, and plate tectonics that erase evidence so efficiently on Earth. Footprints left on the lunar surface, remarkably, could persist for tens of millions of years or longer, slowly worn down only by the extraordinarily gradual bombardment of microscopic space dust, since there is no wind and no rain there to wash them away. In a strange twist, the most durable and long-lasting monument our current civilization is likely to leave behind might not be anything on Earth at all. It might be a handful of footprints, pressed into gray lunar dust, on a world we visited only briefly, and then left almost entirely alone. The formal version of this idea was published as a serious academic paper by a climate scientist named Gavin Schmidt and an astrophysicist named Adam Frank, appearing in a peer-reviewed astrobiology journal. The playful name they chose, the Silurian hypothesis, was actually borrowed directly from an old British science fiction television series, which had imagined an ancient reptilian civilization living deep underground on Earth, long before humans existed. The scientists were careful to point out, almost immediately, that the name was meant affectionately and somewhat humorously, and that they were not endorsing anything resembling the fictional premise. They simply needed a memorable label for a very real and very testable scientific question, and the borrowed name stuck. When the paper was released, it produced an unusually wide range of reactions for what was, at its heart, a fairly narrow and careful piece of reasoning about sedimentary geology and detection limits. Some outlets and commentators ran with sensational headlines, suggesting that scientists believed a lost civilization had actually existed, which was a significant overstatement of what the paper actually argued. Other scientists in the fields of geology and paleontology pushed back, pointing out, correctly, that every other line of evidence we possess about the history of life on Earth strongly supports humans being the first and only species to develop industrial technology on this planet. The fossil record of brain-size evolution across the primate lineage, the well-documented and gradual development of tool use across millions of years, the complete absence of any anomalous artifact ever discovered inside undisturbed ancient rock strata. All of it lines up consistently with the straightforward and far simpler explanation that we are, in fact, the first. But Schmidt and Frank were not actually trying to argue against that conclusion. Their real purpose was almost entirely methodological, aimed less at Earth's distant past and more at a very practical, forward-looking problem, namely, how future missions searching for life on other planets should think about the kinds of evidence that would or would not survive over enormous stretches of geological time. Their paper became something of a quiet touchstone within the field of astrobiology, precisely because it forced scientists to think carefully and explicitly about detection limits, rather than assuming that any past biological or technological activity would automatically leave behind something we could recognize. It reframed a question that sounds almost like a campfire story. Could dinosaurs have built cities into a genuinely rigorous exercise in statistics, sedimentology, and the physics of long-term chemical preservation? What makes the story even more interesting is how the idea has continued to circulate well beyond the original scientific paper, showing up in popular science articles, documentary-style videos, and casual conversations among people who love thinking about deep time. Most of that popular retelling loses the careful hedging and nuance of the original academic argument, sliding toward a more dramatic framing that suggests scientists suspect something might really be buried out there. The truth is more modest and, in its own way, more remarkable. Two credentialed scientists looked honestly at the physical limits of their own field, admitted candidly how little of the deep past actually survives to be examined, and used that admission to sharpen the tools we will need when we eventually turn our full attention towards searching other worlds for signs of life that came before us, or alongside us, somewhere else in the galaxy. It is worth pausing here to separate two ideas that people often blend together without realizing it: intelligence and industry, because they are not the same thing at all, and the distinction matters enormously for this whole discussion. Intelligence, in the sense of complex problem-solving, memory, and social behavior, has actually evolved independently many times across the history of life on Earth, which is itself a remarkable fact. Octopuses and other cephalopods display startling problem-solving ability and short-term memory, despite belonging to a lineage that split off from our own branch of the animal kingdom hundreds of millions of years ago, long before anything resembling a backbone had even appeared. Certain birds, crows, and ravens in particular, solve multi-step puzzles, plan for future needs, and even appear to hold something resembling grudges against specific individuals who have wronged them, all while carrying a brain built on an entirely different structural plan than the mammalian brain we share with elephants, dolphins, and each other. None of these remarkably intelligent lineages, however, ever developed anything resembling industrial technology, and the reasons why are almost as instructive as the intelligence itself. Octopuses live almost their entire lives underwater, where fire simply cannot exist, and fire turns out to be a nearly indispensable ingredient for metalworking, ceramics, and eventually every later stage of industrial development. Birds, for all their cleverness, lack the kind of flexible, strong, precision-capable grasping limbs that allowed our own ancestors to shape stone, tie knots, weave fiber, and eventually build complex machines, since a wing, however useful for flight, is a poor substitute for a hand with an opposable thumb. Dolphins, similarly intelligent and highly social, live in an aquatic environment that makes sustained fire, smelting, and the kind of permanent physical construction humans rely on almost entirely impossible. This suggests that industrial technology is not simply a natural, inevitable consequence of intelligence increasing over evolutionary time. It appears to require a fairly specific and somewhat unlikely combination of circumstances layered on top of intelligence itself. A land-dwelling body plan, manipulator limbs capable of fine motor control, access to fire, a long enough lifespan and social structure to pass complex accumulated knowledge down across many generations, and, crucially, an environment stable enough for that accumulated knowledge to keep building rather than being wiped out repeatedly by catastrophe before it could compound into anything lasting. Humanity appears to be the first lineage on this particular planet where every one of these specific conditions happen to align at once, which is either a remarkable coincidence, an inevitable outcome given enough time and enough attempts, or possibly evidence that it has quietly happened before, in a way we simply have not yet found convincing evidence for. And given everything we have already discussed about how efficiently this planet erases its own past, that final possibility is not nearly as far-fetched as it might initially sound. This is precisely why the Silurian hypothesis resists an easy final answer. It does not hinge on a single missing fossil or a single unexplained rock formation waiting to be discovered in some remote desert. It hinges on the deeper, more uncomfortable observation that the kind of evidence capable of definitively settling the question, one way or the other, might simply not exist anymore, regardless of whether the event itself ever actually happened. Absence of proof, in a system this leaky and this forgetful, cannot honestly be treated as proof of absence, no matter how strongly our intuition wants to reach that comforting conclusion. There is a genuinely strange chapter in Earth's real history that illustrates just how uneven and accidental preservation can be. And it involves the enormous coal deposits that power a large share of the modern industrial world. Around 350 to 300 million years ago, vast, swampy forests spread across huge portions of the planet, filled with towering plants unlike anything alive today. Some of them distant relatives of modern ferns and mosses, grown to the size of large trees. When these plants died, their remains piled up in wet, low-oxygen swamps, layer after layer, for tens of millions of years. Under normal circumstances today, dead plant material is broken down fairly efficiently by fungi capable of digesting a tough structural molecule called lignin, the substance that gives wood its rigidity. But during this particular era, many scientists believe that fungi capable of efficiently breaking down lignin had not yet evolved or had not yet become widespread, meaning that dead trees and plant matter simply did not decompose the way they do now. Instead of rotting away and returning their carbon to the atmosphere, this plant material piled up, undecomposed, for an extraordinarily long stretch of geological time, eventually compressing under its own weight and the weight of sediment above it into the coal seams we mine today. This period left behind an unusually thick and generous record precisely because of an accidental biological gap, a brief window before decomposition caught up with plant evolution. And it is a wonderful reminder that what survives in the rock record often has very little to do with how important or interesting an era actually was, and everything to do with a peculiar and sometimes accidental set of chemical circumstances. Compare that to almost any other stretch of Earth's history involving soft-bodied organisms or land-based ecosystems without such a fortunate accumulation loophole, and you find records that are comparatively thin, patchy, and full of enormous, silent gaps. This unevenness is exactly the trap that the Silurian hypothesis warns us about. We tend to build our mental picture of the deep past almost entirely from the small number of eras that happen to preserve exceptionally well, whether through a swampy coal-forming accident, a sudden volcanic ashfall that buried an entire ecosystem in an instant, or a rare, calm, oxygen-starved seafloor where scavengers could not reach a fallen creature before sediment buried it. Everything else, the vast majority of Earth's history, exists as comparative silence, not because nothing important happened there, but because the specific chemistry and geology of that particular stretch of time simply did not favor preservation. A hidden civilization, existing briefly during one of those silent stretches, could theoretically vanish into exactly the same kind of gap that has already swallowed the overwhelming majority of species that ever lived, industrial or otherwise. The same logic reaches outward, too, well beyond our own solar system, into the growing modern search for what astronomers now call technosignatures. Detectable signs of technology in the atmospheres, or light of distant planets orbiting other stars. Space telescopes capable of studying the faint chemical fingerprint of starlight passing through a distant planet's atmosphere are, even now, beginning to search for gases that industrial activity produces in unusually large quantities, certain synthetic compounds, unusual combinations of oxygen and methane existing together in proportions that natural biology alone struggles to explain, or pollutants that essentially require deliberate manufacturing to exist in noticeable concentrations. But the Silurian hypothesis casts a long, quiet shadow over this entire search, because it reminds us that a technosignature is not a permanent feature of a planet. It is a narrow, brief flash, chemically speaking, that appears only while a civilization is actively industrial, and then fades, sometimes remarkably quickly. Once that civilization either collapses, depletes its accessible fuel sources, or transitions to something cleaner and quieter that no longer produces an obvious atmospheric footprint. If we happen to observe a distant planet, a mere few million years, or even a few thousand years, after its own industrial civilization faded away, its atmosphere might already look almost entirely unremarkable again, its rivers and oceans slowly diluting and burying whatever chemical trace had briefly marked their presence, exactly the way Earth's own atmosphere would likely recover and normalize within a relatively short span of time if humanity vanished tomorrow. This helps frame one of the most haunting open questions in modern astronomy, sometimes called the Great Silence. The simple observation that, despite decades of listening for radio signals and increasingly sophisticated searches for atmospheric technosignatures, we have not yet found a single confirmed sign of another technological civilization anywhere in the universe. Optimists point out that our searching has, so far, covered only an infinitesimally small slice of the sky, the radio spectrum, and cosmic time, and that patience and better instruments will eventually change the picture. But the deep time argument adds another layer entirely to that silence. Even if intelligent technological life has arisen many times across the history of the galaxy, the odds of any two such civilizations existing during an overlapping window narrow enough for their signals to actually reach each other could be extraordinarily small, especially if each civilization's detectable industrial phase lasts only a few thousand years out of a galaxy that has existed for over 10 billion. Under this framing, the galaxy might not be silent because it is empty. It might be silent because it is full of brief, scattered flashes of activity, separated from each other by such enormous gulfs of time and distance that almost none of them ever line up closely enough to notice one another, each flash rising, burning briefly, and fading back into the same kind of geological and chemical quiet that swallows nearly everything, given enough time. It is a strange kind of loneliness to consider, not the loneliness of true emptiness, but the loneliness of near misses stretched across deep time. Civilizations that may have existed in abundance, yet almost never close enough, in either space or time, to ever say hello to one another. There is a symmetry hiding inside this entire discussion that deserves its own moment of attention, because it reframes the whole question of past civilizations in a way that feels less like a mystery and more like an inevitability worth sitting with. Just as an enormous stretch of Earth's past lies mostly hidden from us, an enormous stretch of Earth's future remains genuinely open. And that future is not infinite either. The sun is slowly, steadily brightening as it ages, a natural consequence of the nuclear fusion process happening in its core, gradually changing its internal composition over billions of years. Roughly 1 billion years from now, the sun will likely be bright enough that it begins triggering a runaway process on Earth, evaporating the oceans and stripping away the conditions that make complex surface life possible. Regardless of anything humanity or any successor species chooses to do about carbon emissions or industrial technology in the much nearer term. Long before the sun ever becomes a red giant and physically swells outward, an event still around 5 billion years away, Earth's surface will likely have already become uninhabitable for complex life as we currently understand it. Set beside that distant deadline, the total span of time during which Earth has supported complex, land-dwelling life, from the first forests to whatever comes after us, spans perhaps 600 million years so far, and might realistically continue for a further 600 million years or so before the sun's slow brightening closes that particular window for good. That gives complex terrestrial life on this one planet a usable stretch of roughly 1.25 billion years, give or take. Out of the more than 4.5 billion years Earth has existed, and out of the more than 13 billion years the universe itself has existed, humanity, industrial and otherwise, occupies a truly minuscule sliver near the very end of that already narrow window. This framing matters enormously for the entire Silurian hypothesis, because it means the question is not really about whether ancient reptiles built cities in some distant, isolated corner of deep time. It is about recognizing that Earth's entire history of complex, land-based life represents only a modest fraction of the planet's total existence, bookended on one side by billions of years of a lifeless or microbial-only world, and bookended on the other side by an eventual future in which the sun itself renders the surface unlivable again. Within that comparatively narrow habitable window, life has already demonstrated an impressive capacity for producing complexity, intelligence, and, in our specific case, industrial technology, in what amounts to a single, brief attempt near the very end of the available time. Whether that attempt has happened once, or whether it has, in some quiet and now thoroughly erased corner of that window, happened before, remains a question the rocks themselves may simply be unable to answer for us, no matter how carefully we ask it. It is worth being very clear about something, because this particular topic sits right on the edge of an area frequently colonized by pseudoscience, and good scientific reasoning depends on keeping that boundary sharp. Over the years, various claims have circulated about strange, supposedly out-of-place objects found embedded in extremely old rock, things like metal fragments allegedly discovered inside coal, or oddly shaped stones claimed to resemble tools, presented online or in sensational articles as supposed proof of an advanced civilization existing millions of years before humans. Almost without exception, when these individual claims have actually been examined carefully by geologists and materials scientists, they turn out to have far more mundane explanations. Natural mineral formations called concretions that can form oddly symmetrical shapes through entirely ordinary chemical processes, misidentified fossils, contamination from more recent material falling into an older excavation site, or, in some documented cases, outright fabrication for attention or profit. The Silurian hypothesis, as originally proposed by actual research scientists, is fundamentally different from these kinds of sensational claims in one crucial respect, and that difference is the entire point. It does not claim that any specific anomalous object has been found. It does not point to a single mysterious artifact and declare it unexplainable. Instead, it starts from an entirely different direction, asking a careful, quantitative question about detection limits, about how much of the relevant rock record actually survives, about how thoroughly we have searched what does survive, and about what kind of chemical signature would even be capable, in principle, of surviving long enough to be found if such a civilization had existed. That is a fundamentally more rigorous and more honest kind of question than simply pointing at a strange-looking rock and declaring it proof of the impossible. Good science, in other words, is often less about finding dramatic answers and more about honestly mapping the boundaries of what we are actually capable of knowing, given the tools and evidence available to us. The Silurian hypothesis is a wonderful example of this kind of intellectual humility, applied rigorously. A group of credentialed researchers essentially saying, before you get too confident in a sweeping negative conclusion like no such civilization ever existed, let us calculate exactly how confident that conclusion is actually allowed to be. Given how much of the evidence has already been destroyed by entirely natural processes, regardless of whether anything was ever there to destroy in the first place. That is a very different and considerably more careful, kind of claim than any of the sensational pseudoscientific stories that occasionally borrow its name for attention. This distinction matters for how we think about extraordinary claims more broadly. Whether the subject is ancient civilizations, distant exoplanets, or anything else at the edge of current knowledge. The exciting version of a story is not always the honest one, and the honest version of a story, patient, hedged, and quantitative as it often is, can still be genuinely fascinating once you take the time to actually understand what it is truly saying, rather than settling for the more dramatic headline that gets shared without context. Interestingly, the tools needed to actually test some of these ideas are improving rapidly, even if no dedicated search program has been built specifically to hunt for an ancient, hidden civilization. Deep-sea drilling expeditions continue to extract long cylindrical cores of sediment from the ocean floor, each one a physical timeline stretching back millions of years, layer by layer, and modern laboratories can now measure isotope ratios and trace chemical concentrations within these cores with a level of precision that would have been unimaginable a few decades ago. Every new core pulled from the sea floor adds another small window into a record that remains, overall, extremely thin compared to the full history it is meant to represent. Machine learning and advanced pattern recognition are also beginning to reshape how scientists search enormous datasets of geological and chemical measurements for subtle anomalies that a human researcher, scanning charts by eye, might simply miss. A sudden and unusual co-occurrence of several chemical markers, appearing together in a narrow band of ancient rock in a way that would be statistically very unlikely to happen by chance, is exactly the kind of pattern that automated analysis is increasingly well suited to flag for closer human review, even across enormous datasets collected from drilling projects scattered around the entire planet. Meanwhile, the search for technosignatures on planets orbiting other stars is advancing on a completely separate front. Space telescopes capable of analyzing the faint light passing through a distant planet's atmosphere are steadily improving their ability to detect and measure the concentration of specific gases that could indicate either biological activity or industrial activity, depending on their exact combination and abundance. Every improvement in this technology effectively extends humanity's search for technosignatures outward, planet by planet, star system by star system, complementing the inward-looking, geological version of the same basic question we have been exploring about our own world's distant past. None of these tools have found anything resembling direct evidence of a prior industrial civilization on Earth, and it remains entirely possible, arguably still the most probable outcome by far, that nothing of the sort will ever be found, simply because nothing of the sort ever existed. But the fact that we now possess instruments precise enough to meaningfully ask the question, and honest enough as a scientific community to acknowledge exactly how limited our current search has been, represents genuine progress, even without a dramatic discovery attached to it. Sometimes the most valuable outcome of a scientific question is not the answer itself, but a clearer, more rigorous understanding of exactly what it would take to actually answer it, and exactly how much confidence we are currently entitled to claim. There is also a very human reason this question tends to provoke such strong reactions, and it has little to do with geology at all. Most of us carry a quiet, mostly unspoken assumption that human civilization represents something singular, a first and perhaps only chapter in the story of intelligence on this planet, and there is a kind of comfort in that assumption. It places us at the beginning of something important rather than somewhere in the middle of a longer, stranger pattern we do not fully understand. But nature, across nearly every other domain scientists have studied carefully, tends to resist the idea of singular, unrepeated events far more often than our intuition expects. Eyes, for example, evolved independently dozens of separate times across the animal kingdom, arriving at strikingly similar optical solutions through completely unrelated evolutionary paths, simply because the underlying physics of focusing light rewards certain shapes and structures, regardless of which lineage stumbles onto them first. Flight evolved independently at least 4 separate times: in insects, in the now extinct flying reptiles called pterosaurs, in birds, and again in bats, each lineage solving the basic aerodynamic problem in its own particular way. Complex image-forming intelligence capable of tool use and social learning likewise appears to have arisen independently in primates, in certain birds, and in cephalopods, 3 lineages separated by hundreds of millions of years of independent evolution, each converging on broadly similar cognitive tricks, because those tricks simply work well for surviving in a complicated world. Given how often evolution seems willing to rediscover the same basic solutions repeatedly across very different lineages and very different eras, it would arguably be more surprising, not less, if industrial-level technology turned out to be a strict, unrepeatable, one-time event in the entire history of a planet that has supported complex land life for over 500 million years. That does not mean it definitely happened more than once. It simply means our instinctive assumption of uniqueness deserves at least a little healthy skepticism, rather than being accepted automatically as the safest or most obviously correct starting point. This is perhaps the quiet, deeper lesson hiding underneath the entire Silurian hypothesis, beyond the specific geology and chemistry involved. It gently challenges a certain kind of unexamined self-importance, the assumption that our moment, our species, our technology must be the special, unrepeated exception to a pattern that nature otherwise seems to enjoy repeating whenever the underlying conditions allow it. Whether or not another industrial civilization ever actually rose and fell on this planet before us, taking that possibility seriously, even briefly, is a useful exercise in humility, the same kind of humility that has repeatedly reshaped human understanding of our place in the universe. From realizing our planet does not sit at the center of the solar system, to realizing our galaxy is merely one among hundreds of billions scattered across an unimaginably vast cosmos. If Earth already erases its own history this efficiently, consider a planet where the situation is even less forgiving. Venus, our sister world in terms of size and composition, is thought by some researchers to have possibly hosted a period of much milder surface conditions billions of years ago, potentially even including liquid water on its surface, before a runaway greenhouse effect transformed it into the crushing, scorching world we observe today. A place where surface temperatures now regularly exceed those needed to melt lead, and where atmospheric pressure alone would crush an unprotected human body almost instantly. Nobody is seriously suggesting that Venus once hosted an industrial civilization, and there is no meaningful evidence pointing in that direction at all. But Venus offers a valuable extreme case study in just how completely a planet's surface history can be rewritten. Its current surface appears to be geologically young across nearly its entire globe, likely resurfaced by a period of intense, widespread volcanic activity several 100 million years ago, an event so thorough that it appears to have erased almost all older surface features across the entire planet in one relatively brief planetary scale event. Whatever Venus's surface looked like 1 billion years earlier, whether it had oceans, weather, or nothing resembling Earth at all, that older surface is almost certainly gone now, melted, buried, and rebuilt from scratch by the planet's own violent internal activity. Compare that to Earth's own more gradual, patchwork erasure through plate tectonics and erosion, spread out steadily over billions of years rather than concentrated into one dramatic resurfacing event, and you begin to appreciate just how differently and how unpredictably different planets treat their own deep past. Some worlds, like Mars, with its calm, largely inactive geological history for the past few billion years, preserve ancient terrain remarkably well, offering scientists a genuinely privileged window into conditions from very early in the solar system's history. Other worlds, like Venus, seem to have wiped their own geological memory almost entirely clean through catastrophic, planet-wide resurfacing. Earth sits somewhere between these two extremes, constantly recycling its own crust through plate tectonics, but doing so gradually enough that pockets of genuinely ancient rock, some dating back over 3 billion years, do occasionally survive in a small number of remarkably stable, ancient regions of continental crust, tucked away in places like parts of Western Australia, Southern Africa, and northern Canada. This comparison across three very different worlds drives home the central idea running through this entire exploration. Whether or not a hidden chapter of complex life or technology exists somewhere in the deep past of any given planet, our ability to actually find and confirm it depends enormously on the specific, sometimes accidental, geological personality of that particular world, how actively it recycles its own crust, how violently it resurfaces itself, and how much of its oldest material happens to survive, tucked away in quiet corners, waiting for someone curious enough and patient enough to go looking. There is a real, well-documented episode from the 1990s that illustrates exactly how difficult it is to correctly interpret ambiguous evidence of ancient life, even when scientists are being genuinely careful and rigorous about it. A meteorite discovered in Antarctica, later confirmed through its chemistry to have originated on Mars, blasted off that planet by an ancient impact, and eventually landing on Earth after drifting through space for millions of years, contained tiny, worm-shaped structures visible under powerful microscopes, along with certain mineral formations that some researchers argued closely resembled structures produced by bacteria on Earth. When the discovery was announced, it made headlines around the world, treated by many as potential evidence of ancient microbial life on Mars, a genuinely historic claim if confirmed. But the scientific community responded with exactly the kind of careful scrutiny that good science demands. Other researchers pointed out that the tiny structures were far smaller than any confirmed bacteria on Earth. So small that some argued there simply was not enough physical space inside them to contain the basic biological machinery any cell would need to function. Alternative explanations involving entirely non-biological chemical processes capable of producing similar shapes without any life being involved at all were proposed and tested. Decades later, the scientific consensus has shifted heavily toward viewing the meteorite's contents as most likely non-biological in origin, though the debate, remarkably, has never been fully and completely settled to everyone's satisfaction, and a small number of researchers still argue the case deserves further examination with newer instruments. This story matters enormously for our broader discussion because it shows, in real and well-documented detail, exactly how easy it is to see a tantalizing, lifelike pattern in ambiguous physical evidence, and exactly how much careful, patient, occasionally contentious scientific work is required to determine whether that pattern reflects something genuinely biological or something entirely mineral and mundane that merely happens to resemble life if you are not careful and rigorous in your analysis. If distinguishing ancient microbial life from ordinary mineral chemistry inside a single small meteorite required decades of intense scientific debate among specialists armed with the best instruments available, imagine how much more difficult it becomes to confidently rule an ancient industrial civilization either in or out based on an even thinner, even more heavily eroded slice of Earth's own deep past. The lesson is not that we should distrust scientific caution or dismiss careful skepticism. Quite the opposite. It is a demonstration of exactly why that skepticism exists and exactly why it matters. Extraordinary claims genuinely do require extraordinary evidence, and the careful, sometimes frustratingly slow process of ruling out mundane explanations before reaching for an exciting one is not scientific timidity. It is the entire reason science manages to be trustworthy at all, even when, as in the case of the Silurian hypothesis, the honest final answer ends up being a careful, hedged acknowledgement of genuine uncertainty rather than a dramatic, satisfying conclusion in either direction. There is a strange, almost recursive twist worth sitting with before we close this journey. Because the exact same problem we have been describing about the deep past applies just as forcefully to our own deep future. If humanity continues, spreading eventually to other worlds, building new societies that might rise, transform, decline, and be replaced many times over across tens of thousands or millions of years, our own distant descendants may eventually face the exact same frustrating puzzle when they try to reconstruct the history of their own earliest ancestors. Records degrade. Digital storage, ironically, tends to be far less durable across truly long timescales than a slab of carved stone, since hard drives, magnetic tape, and optical discs all decay chemically within decades or centuries without active maintenance and copying, whereas a message carved deeply into hard granite can, in principle, remain legible for tens of thousands of years with no maintenance at all. This is not merely an abstract curiosity. It has already shaped real, serious, engineering discussions among scientists, tasked with an unusual and slightly eerie responsibility: designing warning markers for deeply buried nuclear waste storage sites, meant to remain clearly understandable for periods of time longer than any human language or civilization has yet lasted, spanning 10,000 years or more into the future. How do you warn a civilization that may not speak any language currently in existence, that may not share any of our current cultural symbols, and that may not even be human in any familiar sense, to stay away from a specific patch of ground because something buried underneath it remains genuinely dangerous? Proposed solutions have included deliberately unsettling architecture designed to provoke instinctive unease regardless of culture, deeply carved pictorial warnings intended to convey danger through universal, non-linguistic imagery, and redundant physical markers built from materials specifically chosen because they resist weathering and erosion for the longest possible stretch of time. If designing a message capable of surviving and remaining meaningful across 10,000 years already counts as one of the more genuinely difficult challenges modern engineers have ever tackled, then it becomes far easier to appreciate exactly how enormous a gap 50 million years or 100 million years actually represents. It is not simply 10,000 years multiplied a few times over. It is many thousands of times longer. Long enough for entire mountain ranges to rise from flat plains and then erode back down to flat plains again. Long enough for oceans to open and close. Long enough for the very shape of the continents on a map to become almost entirely unrecognizable compared to how they look today. Perhaps, in a quiet and unexpectedly practical way, the deepest lesson of the Silurian hypothesis is not really about the distant past at all. It is a gentle, well-reasoned warning aimed squarely at our own future, a reminder that anything we genuinely want remembered, whether a warning, a discovery, or simply the plain fact that we existed at all and thought carefully about the universe around us, cannot be left to chance, cast casually into paper, plastic, or fragile electronic memory, and simply hoped into permanence. If we want to be found, understood, and correctly interpreted by whoever or whatever comes long after us, we may need to think and build with the same patient, geological timescale that the rocks themselves operate on, rather than assuming, the way every civilization before an ending tends to assume, that someone will simply remember. It helps, at this point, to look at an example of deep time evidence that genuinely did survive cleanly and completely, because it shows exactly what convincing proof looks like when the geological conditions cooperate. And it highlights, by direct contrast, just how different that is from the murky uncertainty surrounding any hypothetical hidden civilization. Around 66 million years ago, an asteroid, roughly the width of a small city, struck the coast of what is now the Yucatan Peninsula, releasing an amount of energy almost impossible to comprehend, triggering wildfires across much of the planet, and throwing enormous quantities of dust and vaporized rock into the atmosphere, blocking sunlight and collapsing food chains around the globe within a remarkably short period of time. That single, catastrophic event left behind a thin, unmistakable layer of rock found today at hundreds of separate sites scattered across every continent, a layer unusually rich in a rare metal called iridium that is uncommon in Earth's crust, but far more common in asteroids, along with tiny glass beads formed from rock, instantly melted and flung skyward by the impact, and a striking, sudden discontinuity in the fossil record directly above and below that thin layer, with an enormous range of species present just below it and then permanently absent just above it. This evidence is considered essentially conclusive by the overwhelming majority of scientists, precisely because it checks every box that ambiguous evidence usually fails to check. It appears consistently at an enormous number of independent sites around the entire globe. It involves a chemical signature, the iridium enrichment, that is exceptionally difficult to explain through any ordinary earthly process, and it lines up in perfect chronological sequence with an abrupt, dramatic, and otherwise unexplained shift in the fossil record. Now, compare that gold standard of evidence against everything we have discussed regarding a hypothetical ancient industrial civilization. There is no equivalent iridium-style layer, no chemical signature found consistently at numerous independent sites around the world, no widely reproduced anomaly that multiple independent research teams have each verified using different samples and different methods. What we have instead is an absence, a lack of any such signature in the comparatively limited slice of ancient rock that has actually been carefully examined so far. That absence is genuinely meaningful evidence, and it is currently the strongest and most honest reason available to believe that no such civilization ever existed. But it is categorically different in strength and character from the overwhelming, globally consistent, chemically unambiguous evidence supporting the asteroid impact that ended the age of the dinosaurs. This contrast is precisely why careful scientists describe the Silurian hypothesis the way they do, not as a claim that something happened, and not even really as a claim that something probably did not happen, but as an honest description of the actual gap between what we currently know and what we could, in principle, ever hope to know, given how the rock record behaves. Real, convincing evidence of past events does exist and does survive when the physical circumstances are generous enough, as the asteroid impact clearly demonstrates. The absence of anything nearly that convincing for a hidden civilization tells us, at minimum, that nothing on the scale of a global, catastrophic, iridium-style event ever marked its ending. It tells us considerably less about whether something smaller, quieter, and more thoroughly erased by ordinary geological processes might once have come and gone. Let's return, for a moment, to where this entire journey began, to that ancient shoreline and the fossilized footprints pressed into stone hundreds of millions of years ago. Those footprints survive purely by accident because a particular patch of mud happened to dry, harden, and become buried under exactly the right conditions before rain, waves, or time could erase it. Multiply that same fragile accident across the entire history of life on this planet, and you begin to understand why the fossil record feels less like a complete archive and more like a handful of surviving photographs pulled from an album that mostly burned. Everything we have walked through, the 200 million year cycle of ocean crust being born and swallowed again, the relentless grinding down of mountains into flat plains, the overwhelming rarity of fossilization itself, the thin and easily erased chemical signatures that even our own loud, metal-hungry, carbon-burning civilization is currently leaving behind, all of it points toward the same uncomfortable and genuinely humbling conclusion. Our confidence that humanity is Earth's first industrial civilization rests on real, solid evidence, the steady, unbroken fossil trail of our own evolution, the complete absence of any anomalous artifact ever discovered in undisturbed ancient rock, and the straightforward biological logic showing how rare and specific the combination of traits required for industry actually is. But that confidence is not, and honestly cannot be, absolute, because the very same planet that would need to preserve evidence of such a civilization is also a planet remarkably good at destroying its own history, methodically, patiently, without any regard for how important or interesting that history might have been. This is not a frightening thought once you sit with it for a while. It is, in its own strange way, a genuinely expansive one. It means the story of complex life on Earth is not simply a straight, single line leading directly and inevitably to us. A story where every previous chapter exists solely as a setup for humanity's arrival. It is instead a story with hidden gaps, silent stretches, and closed doors, some of which we will likely never manage to open, no matter how sophisticated our instruments eventually become. There is something almost humbling and beautiful about a universe patient enough and forgetful enough to erase entire chapters of its own past so thoroughly that even a species clever enough to build telescopes, dig up dinosaur bones, and split the atom still cannot say with total, complete certainty whether it was the very first of its kind to walk this particular stretch of cosmic ground. And this uncertainty stretches outward too, well past the edges of our own small planet, into every other world we are only just beginning to study seriously, into the ongoing search for chemical fingerprints of biology or industry in the atmospheres of distant exoplanets, into the quiet, patient drilling projects, pulling ancient sediment up from the floor of our own oceans, and into the growing, unresolved question of why, after decades of listening, the wider universe still has not answered us back. Perhaps it never will. Perhaps, more strangely, it already has, in a language written entirely in isotope ratios and buried mineral chemistry, a language we simply have not yet learned to read closely enough, on our own world or on any other. There is a genuinely fascinating, and often misunderstood, real scientific thought experiment from decades ago that deserves mention here, since it approaches a very similar question from an entirely different angle, not asking whether an ancient civilization already existed, but asking what might have happened if the age of dinosaurs had simply continued a little longer without the asteroid impact that ended it. In the late 1970s and early 1980s, a paleontologist studied a small, fast, unusually large-brained dinosaur called Troodon, a lightly built predator with forward-facing eyes, grasping hands, and, relative to its body size, one of the largest brains of any dinosaur yet discovered. extrapolating that gradual trend of increasing relative brain size forward across many additional millions of years. Had the extinction event never occurred, the paleontologist proposed a speculative, deliberately illustrative model, sometimes nicknamed the dinosauroid, an imagined descendant with an upright posture, forward-facing eyes for depth perception, and dexterous, grasping hands, potentially capable of manipulating tools, not because any actual fossil evidence shows this happened, but purely as an exercise in extrapolating an existing, well-documented evolutionary trend forward in time. The proposal was always presented as speculative and illustrative rather than as an actual scientific claim about history, and it has been revisited, refined, and gently criticized by other paleontologists many times since, particularly regarding exactly how much larger that brain trend would realistically have grown given more time, and whether other biological or environmental factors would have interrupted or redirected it long before anything resembling true intelligence emerged. But the exercise remains genuinely valuable, precisely because it demonstrates something important running through this entire discussion. There is nothing biologically implausible, in principle, about a reptilian lineage slowly trending toward larger relative brain size, improved depth perception, and increasingly dexterous forelimbs, the same basic ingredients that eventually contributed to primate intelligence along an entirely separate evolutionary branch. Evolution does not care which lineage gets there first, or whether the resulting creature has fur, feathers, or scales. It only cares whether a particular combination of traits happens to provide a survival advantage generation after generation, for long enough without being interrupted. This connects directly back to the playful name borrowed for the Silurian hypothesis itself, since the fictional television reptiles that inspired the name were imagined as exactly this kind of alternate evolutionary outcome, an intelligent, technological lineage descended from reptiles rather than mammals. The real science behind both the dinosauroid thought experiment and the Silurian hypothesis converges on the same underlying, genuinely important idea: that intelligence and eventually technology are not the exclusive property of any one particular branch of the evolutionary tree, mammalian, reptilian, or otherwise. Given enough uninterrupted time and the right specific combination of pressures, multiple different lineages across Earth's long history plausibly could have arrived somewhere resembling the destination our own particular branch happened to reach first. Or perhaps, if the deep, thoroughly erased past is stranger than we currently know, somewhere similar to a destination another branch may have already quietly reached before us, long before leaving anything behind that we have yet managed to find. It is also worth considering a quieter, less dramatic possibility than a full industrial civilization, because the geological detectability problem applies just as strongly here, and it is grounded in evidence we already have rather than pure speculation. Humanity is not, and has never been, the only member of our own genus to walk upright, use tools, and organize into complex social groups. Several other closely related species have existed alongside or before us, and some of what we are learning about them continues to surprise even specialists. A relatively recently discovered species known as Homo naledi, identified from remains found deep within a cave system in southern Africa, appears, based on ongoing and still actively debated research, to have deliberately placed the bodies of its dead in hard-to-reach chambers deep underground, a behavior that, if confirmed, would suggest a level of intentional, symbolic behavior around death that scientists once assumed belonged only to our own direct lineage. This species had a notably smaller brain than modern humans, roughly a third the size, and yet may have engaged in behavior previously considered a hallmark of much larger-brained, more cognitively sophisticated hominins. The debate among specialists over exactly how to interpret this evidence remains lively and unresolved, precisely because the evidence itself, pulled from one difficult-to-access cave system, is inherently limited, a small window into a much larger and largely invisible pattern of behavior we simply cannot fully reconstruct from what little happens to survive. This matters enormously for our broader discussion because it shows, using real, tangible fossil evidence rather than pure hypothetical reasoning, how easily an entire dimension of a past species' behavior and cognitive complexity can remain hidden, ambiguous, or entirely undiscovered for an extraordinarily long time, simply due to the accident of where and how their remains happen to be preserved. If a relatively recent, closely related hominin species can carry this much lingering uncertainty about its own symbolic behavior, discovered only because of one unusually well-preserved and unusually deep cave system, imagine how much uncertainty must surround species and lineages far more distant from us in time, buried under far less generous preservation conditions, or not preserved at all. None of this requires us to imagine an industrial civilization to find the underlying point compelling. A species could have developed rich oral storytelling traditions, complex social structures, sophisticated cooperative hunting strategies, or even early symbolic art using entirely biodegradable materials like wood, plant fiber, and pigment, and left behind almost nothing that would survive for a fraction of a million years, let alone tens of millions. Culture and complexity do not require metal, concrete, or a chemical signature detectable in ocean sediment. They can exist, flourish, and eventually vanish, leaving behind only the same kind of comparative silence that swallows the overwhelming majority of everything that has ever lived on this restless, forgetful, endlessly recycling planet. Suppose, for a moment, that someday, a research team drilling into 50-million-year-old sediment somewhere on Earth actually did find something strange. An unexplained isotope anomaly, an unusual concentration of a rare metal, or some other chemical signature that did not fit comfortably within known natural processes. What would it actually take, scientifically, for that single strange finding to become genuinely convincing evidence of an ancient civilization, rather than simply another unexplained natural oddity added to the long list of geological puzzles that already exist without any exotic explanation required? The first requirement would be reproducibility across multiple independent sites. A single strange sample from a single narrow drill core, however intriguing, could always be explained by contamination, an unusual local mineral deposit, or a rare but entirely natural chemical process specific to that one location. Only if the same anomaly appeared consistently, at the same approximate point in geological time, across numerous separate and independently studied locations around the globe, would the pattern start to resemble the kind of globally distributed, chemically consistent signal we discussed earlier regarding the asteroid impact that ended the age of the dinosaurs. The second requirement would be a plausible explanatory mechanism ruling out known natural processes. Scientists would need to systematically test and eliminate volcanic activity, unusual ocean chemistry, biological processes, and every other known natural pathway capable of producing a similar signature, the exact same rigorous elimination process that took decades to work through regarding the ambiguous Martian meteorite discussed earlier. Only after exhausting the most plausible natural explanations would an artificial origin become scientifically reasonable to seriously consider. And even then, most careful scientists would likely reach first for an unusual, previously unrecognized natural process rather than jumping directly to the far more extraordinary conclusion of a hidden civilization. The third and perhaps most demanding requirement would be internal consistency with a coherent story. A genuine ancient civilization would not produce just one isolated anomaly. It would very likely leave behind a cluster of related signals appearing together within the same narrow window of geological time, an unusual carbon isotope shift alongside an unusual nitrogen signature, alongside a synthetic molecule that resists any known natural explanation, alongside a sudden and otherwise unexplained shift in the fossil record, mirroring, in miniature, the same kind of layered, mutually reinforcing evidence that currently supports our own Anthropocene boundary as a real and measurable feature of the geological record. Meeting all three of these demanding requirements simultaneously, global reproducibility, elimination of natural explanations, and a coherent cluster of mutually reinforcing signals, would be an extraordinarily high bar to clear, and rightly so. Nothing discovered so far has come remotely close to clearing it, which is precisely why the scientific consensus remains firmly settled on humanity being Earth's first industrial civilization. But understanding exactly what convincing evidence would actually require, in careful, itemized detail, is itself a valuable outcome of this entire thought experiment, because it transforms a vague, speculative question into something scientists could genuinely test against, layer by layer, drill core by drill core, for as long as curiosity and funding allow the search to continue. There is one more angle worth exploring before we bring this journey to a close, and it concerns not the past or the future, but the present moment and the peculiar value of asking a question that may never receive a fully satisfying answer. Some scientific questions get resolved cleanly within a single career, a hypothesis proposed, tested, confirmed, or rejected, textbooks updated accordingly. Other questions, like this one, seem destined to remain permanently open, not because scientists are careless or unimaginative, but because the physical evidence required to close the question definitively may simply no longer exist anywhere on the planet. Regardless of how long we keep searching or how sophisticated our instruments eventually become. It would be easy to dismiss a permanently unresolved question as a waste of scientific attention, better spent on problems with clear, achievable answers. But that dismissal misses something important about how scientific understanding actually advances. The Silurian hypothesis has already produced genuine, lasting value, even without resolving its central question, by forcing careful, quantitative thinking about detection limits that now directly informs how we search for biosignatures on Mars, how we interpret potential technosignatures on distant exoplanets, and how we think about the reliability of our own deep time conclusions more generally. A question does not need a clean, final answer to be worth asking seriously. Sometimes the disciplined process of trying to answer it, mapping exactly what we know, what we do not know, and why the boundary between those two categories sits precisely where it does, produces insight and rigor that a tidier, more easily resolved question never could have delivered. There is also something quietly valuable, on a purely human level, in learning to sit comfortably with genuine uncertainty rather than rushing toward a comforting, confident answer in either direction. It would be intellectually lazy to declare with total, absolute certainty that no civilization existed before us, given everything we now understand about how efficiently this planet erases its own past. It would be equally lazy and considerably less scientifically responsible to declare that one probably did exist simply because the idea is dramatic and captures attention more easily than careful hedging ever could. The genuinely honest position, the one careful scientists actually hold, sits in the more uncomfortable middle, acknowledging real uncertainty, following the actual evidence wherever it currently points, which today points firmly toward humanity being first, while remaining fully aware of exactly how much of the relevant evidence has already been permanently destroyed by processes that had nothing to do with truth or falsehood, only chemistry, pressure, and time. That kind of disciplined humility, the willingness to say clearly what we know, what we do not know, and why the difference matters, might be one of the most valuable habits of mind a person can carry away from a story like this one, far more valuable, in the long run, than any single dramatic answer about lizards, cities, or lost civilizations ever could be. Picture, one last time, a research vessel anchored somewhere in the middle of a vast, featureless stretch of open ocean, far from any coastline. Its crew slowly lowering a long metal drilling apparatus down through several thousand meters of dark water toward the sea floor below. The drill bites into layer after layer of ancient sediment, pulling up a continuous cylindrical core, each centimeter representing hundreds or even thousands of years of quiet, undisturbed accumulation, mud settling gently onto mud, generation after generation, for tens of millions of years without interruption. Somewhere within a core exactly like this one, real scientists have found the actual physical evidence of the ancient thermal maximum we discussed earlier, a genuine, dramatic climate event captured in a thin, precisely dated band of unusual chemistry, sitting quietly within an otherwise unremarkable stretch of gray mud. That evidence sat there, undisturbed and unread, for 56 million years before anyone with the right instruments and the right question finally came along to notice it. It is worth remembering that we only found it because we were specifically looking, drilling into exactly the right depth, in exactly the right location, and running exactly the right chemical tests on a material that, to an untrained eye, would look like nothing more than ordinary gray mud. This is perhaps the most important practical lesson buried inside the entire Silurian hypothesis. Evidence does not announce itself. It does not glow, or sparkle, or otherwise call attention to its own significance. It waits, patiently, indistinguishable from everything around it, until someone brings the right question, the right instrument, and the right amount of patient, careful attention to precisely the right sample. The ancient thermal spike was there the entire time, for the 56 million years spanning its formation to its rediscovery, utterly indifferent to whether anyone ever noticed it. If an ancient industrial civilization ever did exist, and if some faint trace of its passing somehow survived the relentless churn of subduction, erosion, and metamorphism that we have described throughout this journey, that trace, too, would simply be waiting, unread, indistinguishable from ordinary rock, for exactly the right combination of curiosity and instrumentation to finally bring it to light. Every layer of sediment on the ocean floor, every ancient outcrop of exposed rock on every continent is, in this sense, a kind of quiet, patient message, written not for us specifically, but simply as an unavoidable byproduct of time passing and chemistry happening, a message that occasionally happens to be legible to whoever eventually arrives with curiosity enough to go looking. We do not yet know everything that message contains. We may never know everything it contains, since so much of the original manuscript has already been destroyed by the same processes that eventually preserved the small fragments we do have. But the search itself, patient, careful, willing to hold uncertainty rather than rushing toward comfortable answers, remains one of the more genuinely beautiful things our species has learned to do with the brief, industrious moment of geological time we currently occupy. It is worth walking, one more time, through the handful of specific stretches of Earth's history that a careful researcher might actually flag as plausible candidate windows, not because any of them show positive evidence, but because they each offer the specific combination of biological complexity and sufficient elapsed time that the thought experiment requires to remain interesting rather than purely theoretical. The first candidate window sits deep in the age of dinosaurs, particularly its later half, when a handful of small, unusually brain-heavy predators, like the one behind the dinosauroid speculation mentioned earlier, were already showing signs of increasing cognitive sophistication, alongside early birds that were rapidly diversifying into an enormous range of ecological niches. This window closed abruptly with the asteroid impact discussed earlier, an ending so well documented and so thoroughly dated that it leaves very little room for a hidden industrial chapter squeezed in immediately beforehand, without leaving any trace in the well-studied layers just below that famous iridium-rich boundary. The second candidate window sits in the tens of millions of years immediately following that same extinction event, when mammals rapidly diversified to fill the ecological space left empty by the departed dinosaurs, producing an explosion of new body plans and behaviors in a geologically short span of time. This is the exact window containing the ancient thermal maximum event discussed earlier, the one so frequently used as the direct comparison case for what an industrial carbon signature might resemble. Because this particular window happens to be relatively well studied by paleoclimatologists, specifically because of that thermal event, it is arguably one of the better examined stretches of deep time available to us. And it still shows no additional signature beyond what natural volcanic or methane release processes can already explain. The third candidate window sits much further back, deep within the age of amphibians and early reptiles, during and after the enormous coal-forming swamp forests discussed earlier. A stretch of time so thoroughly reshaped by plate tectonics since then, that very little of the original ocean floor sediment from that era survives anywhere on the planet today, making this window, ironically, one of the least examined, despite being one of the longest-lasting stretches of complex land-based ecosystems in Earth's entire history. The fourth and final candidate window, more speculative still, sits within the long, quiet stretch of time following the more recent asteroid impact, spanning the tens of millions of years of mammalian diversification that eventually, through an entirely separate and much later branch, produced primates, and much later still, our own particular lineage. Every step of that particular branch's history happens to be unusually well documented compared to the other windows, precisely because it leads directly to us, giving paleontologists a strong, specific motivation to study every fossil bed along that particular path in painstaking detail, leaving comparatively little room, statistically speaking, for an entirely separate, undiscovered industrial chapter to have unfolded quietly alongside it without leaving any trace in the specific fossil beds we already understand so well. None of these four windows currently show anything resembling the kind of evidence that would meaningfully support the existence of a prior civilization. And the overwhelming weight of everything we currently understand about the specific evolutionary path leading to human intelligence continues to support humanity's position as Earth's first industrial species. But naming these specific windows individually, rather than treating the entire question as one vague, undifferentiated blur of deep time, is itself useful, because it transforms an admittedly speculative thought experiment into something considerably more concrete, a list of specific, testable stretches of geological history, each with its own particular preservation quality, its own specific gaps, and its own specific reasons for either confidence or lingering uncertainty. Step back far enough, And this entire question about a possible hidden civilization on our own planet turns out to be a small, local instance of one of the largest and most important questions in all of science. The question of how confidently we can ever claim knowledge about something we cannot directly observe, whether that unobservable thing sits 50 million years in our own past or many light years away around a distant, unreachable star. Both situations share the exact same underlying structure. We have a limited, imperfect sample of evidence. We have a set of physical processes that actively work to destroy or obscure additional evidence over time. And we have a natural human tendency to reach for confident, tidy conclusions well before the evidence genuinely justifies that level of confidence. Good science, the kind practiced by the researchers who first proposed this entire thought experiment, involves resisting that tendency, deliberately and repeatedly, even when resisting it feels unsatisfying, compared to simply announcing a clean, definitive answer. It involves sitting with open, carefully bounded uncertainty long enough to map its edges precisely, rather than rushing past that uncertainty toward whichever answer feels more comfortable, more exciting, or more likely to generate attention. This is precisely why the honest version of the Silurian hypothesis reads less like a bold claim and more like a careful list of caveats. Precisely calibrated statements about detection limits, sampling problems, and comparative evidence quality, each one narrowing down exactly what we are and are not currently entitled to say with confidence about our planet's distant past. This same careful, patient posture is exactly what modern astrobiology increasingly demands as our instruments grow more capable. When a space telescope eventually detects an unusual combination of gases in the atmosphere of a distant planet, the temptation to immediately declare it evidence of alien industry or alien biology will be enormous. Fueled by genuine excitement, media attention, and simple human hope that we are not alone in the universe. Resisting that temptation long enough to systematically rule out every plausible natural explanation, exactly the same disciplined process that took decades to work through regarding the ambiguous Martian meteorite discussed earlier, will likely determine whether humanity's eventual first confirmed detection of extraterrestrial life, whenever it finally happens, is remembered as a rigorously earned scientific triumph or as an embarrassing overreach, later walked back under closer scrutiny. In this sense, learning to ask patient, carefully bounded questions about our own planet's distant past is not merely an interesting historical curiosity. It is direct, practical training for the exact kind of intellectual discipline humanity will need when we eventually confront genuinely ambiguous evidence from somewhere else entirely, whether that evidence arrives from a Martian rock sample, a distant exoplanet's atmospheric spectrum, or some other unexpected corner of the universe we have not yet learned to examine closely enough. The Silurian hypothesis, born from a fairly narrow question about ancient Earth, turns out to be quietly preparing us for one of the most consequential moments our species may ever face. The moment we finally have to decide, carefully and honestly, whether a strange signal from somewhere else in the cosmos is a message, a coincidence, or simply another quiet, indifferent pattern written by chemistry and time, indistinguishable at first glance from everything ordinary surrounding it. There is one final thread worth pulling before we close. And it has less to do with rock layers and more to do with the strange fact that a species barely 300 years into its industrial existence has already found the time, the resources, and the curiosity to seriously ask whether something like itself might have quietly come and gone before it ever arrived. That impulse, to look backward across an almost incomprehensible gulf of time and wonder honestly whether we are truly first, says something meaningful about the kind of creature we happen to be. Most species that have ever lived on this planet spent their entire existence responding only to the immediate demands of survival, finding food, avoiding predators, raising offspring, with no capacity or need to wonder about deep time, ancient sediment, or hypothetical civilizations buried tens of millions of years in the past. Humanity, for reasons that remain genuinely remarkable and only partially understood even by the scientists who study our own evolution most closely, developed something extra. A drive to ask questions that provide no direct survival advantage at all. Questions about where we came from, whether we are alone, and whether anything like us existed before we did. That drive built the very instruments, the drilling rigs, the mass spectrometers, the space telescopes, capable of even asking the Silurian hypothesis seriously in the first place. And it is the same drive currently reaching outward toward other planets and other stars in the ongoing search for life beyond our own world. It is tempting, sometimes, to feel a kind of quiet disappointment at how much uncertainty remains woven through nearly every big question explored in this journey, whether about ancient civilizations, distant exoplanets, or the eventual fate of our own industrial age. But that lingering uncertainty is not really a failure of the search. It is closer to an honest, accurate reflection of how genuinely large and old the universe actually is compared to the brief, specific window during which any one curious species gets to look around and ask questions before its own particular chapter eventually closes. We happen to occupy an unusually good moment for asking these particular questions, equipped with drilling technology capable of reaching deep into ancient sediment, telescopes capable of studying the atmospheres of worlds, orbiting other stars entirely, and just enough accumulated scientific knowledge to understand precisely how limited our current evidence actually is, without yet possessing every tool we would eventually need to close every remaining gap completely. That combination, genuine capability paired with genuine, well-understood uncertainty, might actually be the most honest and most exciting place for a curious species to stand. Not at the triumphant end of a completed investigation, with every question neatly answered and filed away, but somewhere earlier and more interesting than that, deep in the patient, unfinished middle of a search that stretches backward into deep time and outward into the wider galaxy, simultaneously, carried forward by nothing more and nothing less than a persistent, deeply human refusal to simply stop wondering. Consider, one last time, how differently this story might read a century from now, once ongoing deep-sea drilling projects have sampled a meaningfully larger portion of the ocean floor than we have managed so far. Once new isotope detection methods reach sensitivities far beyond what current laboratories can achieve, and once space telescopes have studied the atmospheres of many thousands of planets orbiting other stars rather than the comparatively small handful examined closely today. It is entirely possible that a century from now, the honest scientific answer to this question will remain exactly the same as it is right now. A careful, hedged acknowledgement that no convincing evidence exists, paired with an equally careful acknowledgement that our search has still only scratched the surface of an almost unimaginably large and largely inaccessible archive. It is also possible, though far less likely given everything currently known, that some future drilling project will pull up a sample containing exactly the kind of reproducible, multiply confirmed, mutually reinforcing cluster of anomalies described earlier, and the entire framing of this story will shift overnight from a patient thought experiment into one of the most significant scientific discoveries in the history of our species. Either outcome would be genuinely remarkable in its own way. A confirmed negative result, extended across a much larger and more thorough sampling of Earth's deep past than we currently possess, would meaningfully strengthen our confidence that humanity truly is this planet's first industrial civilization. Closing the question about as tightly as an inherently limited geological record ever allows a question to be closed. A confirmed positive result would rewrite our entire understanding of life's history on this planet, forcing an honest reckoning with the fact that intelligence, technology, and industry are not the singular, unrepeated achievement of one fortunate lineage, but instead a pattern the biosphere is capable of producing more than once, given enough uninterrupted time and the right accumulating conditions. Whichever direction future evidence eventually points, if it ever points clearly in either direction at all, the underlying discipline this entire question has already taught us remains valuable regardless of the final answer. A patient willingness to examine exactly how much confidence a given piece of evidence actually earns, rather than assuming, comfortably and prematurely, that the absence of an easy answer means there is nothing left worth carefully, honestly investigating. It is worth remembering, too, that the search itself is already teaching us things independent of whichever final answer eventually arrives. Every drill core pulled up from the ocean floor adds to a growing global map of ancient sediment chemistry, useful for understanding past climate shifts, ancient ocean circulation patterns, and the long-term behavior of the carbon cycle, entirely apart from any question about hidden civilizations. Every improvement in isotope detection sensitivity, originally motivated in part by this kind of speculative question, ends up sharpening tools used across dozens of unrelated fields. From tracking modern pollution sources to dating archaeological artifacts with greater precision. Curiosity aimed at an admittedly unlikely possibility has a habit of paying unexpected dividends elsewhere, quietly improving the instruments and methods available for entirely different, more immediately practical scientific questions. And it is worth sitting, briefly, with the peculiar fact that asking this question at all required an enormous chain of unlikely events lining up in our own favor. Complex chemistry assembling into life, life surviving repeated mass extinctions across billions of years, one particular lineage of primates developing exactly the right combination of hands, diet, and social structure, and that same lineage eventually building drilling rigs, mass spectrometers, and space telescopes capable of turning a campfire-style question into a rigorous, testable, scientific hypothesis. Every step along that chain could easily have gone differently, and in an enormous number of alternate versions of Earth's history, it very likely did. So where does that leave us? Standing at the end of this particular journey through deep time, it leaves us on a planet that has been quietly recycling its own crust for billions of years, folding continents into mountains, and then grinding those same mountains back down into flat, forgetful plains. It leaves us holding a fossil record that captures only the barest sliver of everything that has ever lived, a record shaped less by importance and more by accident. By which swamp happened to bury which forest, by which seafloor happened to stay calm, long enough for a body to settle gently into mud rather than being scattered by scavengers and currents. It leaves us with a species, our own, that has existed in any recognizable form for only a tiny fraction of the time complex life has walked this planet's surface, an industrial for only the smallest, most recent sliver of even that short span, already leaving behind a strange and measurable chemical signature in rock, ice, and ocean sediment that some future observer, human or otherwise, might eventually dig up and puzzle over the exact same way we now puzzle over an ancient carbon spike buried 56 million years deep in quiet gray mud. And it leaves us with an honest, carefully bounded uncertainty about whether we are the very first to reach this particular point, or whether something else, long before us, reached somewhere similar and then vanished so completely and so thoroughly that the planet itself no longer remembers. There is no need to find that uncertainty unsettling. If anything, it deserves to feel expansive, a quiet invitation to hold our own moment a little more lightly and to look a little more carefully at the ground beneath our feet, knowing that ordinary-looking rock, ordinary gray mud pulled up from the sea floor, might be the only witness left for events that once mattered enormously to whoever or whatever lived through them. Somewhere out there, in a layer of stone nobody has drilled into yet, or perhaps in a layer that has already been swallowed entirely by the slow, patient churn of plate tectonics, an answer may or may not be waiting. We may never know which. And there is a strange, quiet peace available in learning to be genuinely at ease with that. Before you go, if this journey through deep time and vanished possibilities gave you something to think about, please like this video and subscribe, since it genuinely helps this channel keep exploring the strangest, most humbling corners of our universe, one careful, patient question at a time. Thank you for spending this time with us tonight, drifting through hundreds of millions of years of quiet, forgetful stone. Now, let the rock settle. Let the question rest gently in the back of your mind rather than the front, and let yourself drift into an easy, peaceful sleep, carried by the same slow, patient rhythm that has shaped this ancient, endlessly rewritten planet for billions of years.